Today, I'm introduce our recent study on the live program analysis for security critical scenarios. So I'm Zhiqiang from Nanjing University. What's the critical, security critical scenarios? So in my talk here, let's consider the daily scenarios like the intelligence drive. So you're sitting in the car with the auto driving enabled, or the private mobile access, or even the some safety critical like scenarios like the control, like the plane control, etc. So those scenarios are definitely very like security or safety critical, and with these scenarios, definitely there are the large-scale complicated software behind it. For example, I show some like software architecture of the modern like auto control software, and those software are usually contains many bugs. But here in this talk, I will focus on two specific categories of bugs. One is the memory vulnerabilities or memory bugs, such as the buffer overflow, the like out of bound, etc. And another is like the related to the concurrency, right? Like the data race, like data lock, etc. Why we care about these particular two categories of bugs? Because they usually, lead to very serious consequences. I'll explain a little bit more. From the like the quantitative perspective, some institutes also report the some study. For example, it is reported that near 70% of serious problems are related to these two categories of bugs. That's a memory vulnerability and a concurrency bugs. But what's the characteristics of these two particular bugs? For example, usually they are vulnerable to attack. This is not like the normal bug, right? You just when the bug triggered, then your software crashed, and then you restart it, and everything is okay, right? But for those memory vulnerabilities, it's not that simple because usually it's silent error. It's like when the bug triggered, the users are unaware, and but this is very serious. But why? Because attackers can actually leverage this vulnerability to do more serious stuff on your software. That's why we think it's more serious. Another characteristic is they are usually hard to reason between the triggering and the manifesting. For example, if you write the programs in C or C++, it's a common practice that you got the memory segmentation fault, but it's really hard to get the root cause because it's common case that the root cause is far away from the crash point. And also, they usually lead to catastrophic results, as I mentioned before. Another thing is they are really hard to reproduce. For example, the concurrency box is tightly dependent on the threat interleaving, right? So all those like characteristics leads to the very special role of these two categories of problems. So how to detect or how to prevent these bugs? There are common like studies or approaches. For example, we can leverage the existing program analysis techniques. But what is the flaws of the traditional program analysis? Let me explain by showing some simple figures to demonstrate the working process of this analysis. Let's look at this picture. The X is you can think the time as the program executes, and the y is the the program state. It could be composed of various values of the variables and the control flows, and each line corresponds to one execution. So given a software, given many inputs, we can get various concrete executions shown as the lines in the picture. And if we consider the yellow part is a forbidden area, meaning once the line reaches the yellow part, then a bug is triggered. So the traditional dynamic testing or fasting analysis approach is quite like we just try some concrete lines, right? But as it's known, we can only explore the limited side of the concrete executions in-house. Therefore, you may introduce high, false negatives, meaning there are many potential execution scenarios you cannot cover. There's another technique called state analysis, which is an alternative to the dynamic one, which is try to examine all the possible executions of the software, but definitely is undecidable. In order to balance the scalability and the precision, they usually adopt the over-approximation, meaning we have to draw like a curve covering the like a subset of the executions, which cover all the possible executions. But as usual, you will include a lot of infeasible paths into this like the curve. Therefore, it's possible you introduce the false positive because there could be overlap between the approximated shape with the forbidden area. So state analysis has the disadvantage of the false positives. Back to our problem, meaning the memory vulnerability and concurrence bugs. Apparently, these two approaches are not really useful or not really tailored because you have to you try to analyze the exponential or infinite possibilities, and which is undecidable and impractical. So what we try to do is we propose a live analysis, meaning that for these two particular problems, what the important thing is try to do the analysis runtime, right? Because as I mentioned before, these two kinds of problems will lead to the silent errors, which is serious which is very vulnerable and made the serious threat to the users. But if we can get this information at runtime, then we can do whatever we want to prevent the exploration. So therefore, for a live analysis, we can achieve the high precision because at runtime we only cover all the execution behavior at runtime and not missing any trigger bugs. And also we prevent the vulnerability from being exploited, and at the same time we can help reproduce or debug the subtle problems, since we can get enough runtime information to understand the bug or reproduce the bug. However, in order to make this really practical, we have to do something to satisfy the requirements. For example, first, we have to maintain that this live analysis is of ultra low runtime overhead, right? Otherwise, it's not applicable by the deployed software or by any software users. So how to do this? in fact, we have several options. One is we can leverage some modern like hardware features to achieve the pretty low overhead information recording. And on the other hand, we have to make sure the analysis is of low latency, meaning that if there is a latency is allowed between the triggering and the reporting, we have to make sure this latency is sufficiently small. So under this solution, we did some attempts. First is about the dynamic tent analysis, where the selective hardware tracing. So tent analysis actually is a particular analysis mechanism which can be used to detect many different kinds of memory vulnerabilities or even security problems. But same as I mentioned before, the general dynamic tent analysis suffers from pretty high runtime overhead, and the static ones suffer from low precision. So in this particular work, we propose a live tent analysis, which adopts a decoupled mechanism, meaning that we propose two phases of the analysis. One is the online runtime, like online information collection. Another is offline, like tent propagation analysis. Why we adopt this mechanism? Because like I mentioned, we first need to guarantee that the analysis is of a pretty low overhead. How to do this? Meaning that we leverage the hardware module to record the minimum number of the minimal information needed for the analysis, and then we collect those information at runtime, and then send them to another core or another machine at the same time, and let the analysis done in a separate machine. But this simple, naive approach, the idea is pretty simple, but implementing it efficiently and precisely is not that simple. We have to face several challenges. For example, the naive hardware tracing still yield high overhead, and the second thing is the hardware tracing results in severe data loss. You can imagine that the speed of the trace generation is almost close to the frequency of the hardware, the CPUs, which is much higher than that of the bandwidth of the memory. So to tackle these challenges, we propose the hard tent, a live tent analysis system, which consists of two key components. One is a runtime selective tracing, and another is a real-time parallel analysis. The runtime tracing stuff is mainly focused on how to pruning away the unnecessary information recorded, right, by leveraging some static analysis, such as the static identification analysis. We try to find the redundant registers, blocks, or loop iteration, and therefore we can just record the minimum essential set of information for the tent analysis. And another part, the real-time analysis part, is mainly to accelerate the offline tent analysis by using like pipelining or the parallel analysis. This is a particular workflow, like I mentioned. So let's look at each part briefly. Firstly, for the selective instrumentation, we propose the static identification analysis. Try to just find some to filter out the unnecessary information by leveraging the static analysis. The insight behind this is because if given a program, if we try to record every register during the program execution, this is a naive way. But in fact, for the register for the value register, usually you can leverage some static information to infer some values from another values. You don't need to record them all dynamically. So that's the main idea behind this pruning. We propose the redundant register elimination, redundant blocks and function elimination, and redundant loop iteration elimination, and we successfully reduce the number of values need to be recorded at runtime. And then after identifying the minimum essential set of information recorded, then we do some binary instrumentation. I try to insert some hardware tracing instructions into the binaries, and then run the program to collect the instrumented value. So having the value collected at runtime, then like I mentioned, we send those information into another machine through the high-speed the memory transfer protocol, such as the RDMA or CXL, and then we propose the parallel decoding and parallel analysis to processing this hardware tracing data and to get the report. So there are a lot of design details and implementation details. If you're interested in, you can check our paper. So mainly there's a parallel tent propagation analysis algorithm to try to identify the tent problems. Okay, we conducted the comprehensive evaluations over a bunch of benchmarks, including some Unix utilities and the spec CPU and some real-world server applications. And let's look at the performance on the with respect to the runtime overhead. Our hard tent introduced about 8% runtime overhead, and the reporting latency is less than 0.5 seconds, which usually is acceptable by the security people. Like if the vulnerability is encountered, and then for attacker, you usually take several seconds for exploration. On that hand, as I mentioned, besides the runtime overhead, the latency is another important stuff, right? So here we propose the parallel decoding and analysis component, try to accelerate this analysis phase. And this figure shows the throughput of decoding and propagation. So as can be seen, when we are using 32 threads, the decoding and tent propagation throughput exceeds or approaches the trace generation rate, meaning that once the trace is generated, we can immediately process it at another machine, at the other machine. And we also done the comparisons against the state of arts. For example, the software-based approach called selective tent, which leverage the pure stat analysis to accelerate to reduce the runtime overhead of dynamic tent analysis, and also some naive hardware tracing without any pruning enabled. As can be seen, utilizing our static analysis and selective tracing, the hard tent can reduce the overhead from 80% to like 8%. And also hard tent outperforms the other state-of-the-art dynamic tent analysis or approaches. This a straight tent and the tent pipe are both the existing dynamic tent analysis approaches. We also verify the effectiveness of our work, meaning that given a number of existing CVEs, whether our approach can detect them or not. So as can be seen, so Heartland successfully detected all the 8 CVEs. So this is the first thing, and by following the same idea, we also do another work which targets at the data race problems. It's a data race monitor for production use. Like given a production software, whether we can find the data race at runtime. So we follow almost the same structure. The heart race is composed of 2 components: the static selection part and the offline analysis part. Due to the time limit, I will not explain more about these details. But let's show the results. We also done some evaluations of the heart race on the commonly used benchmarks, and also some real-world applications. So this column with the right rectangle shows the runtime overhead of heart race. So on average, it only introduced 1.6% runtime overhead to the subject software. This number is pretty low. I think is totally acceptable by most production run scenarios. And again, we also conducted a detection capability. We reproduce a set of non-data race bugs, and as can be seen, heart race can detect all of them. And we compared with some existing work. One is called ProRace, which do some probabilistic like sampling. They just record some execution in a sample way, and then try to identify the data race. And under each sampling rate, you can see they can detect different numbers of bugs. The right-hand side, the card is another approach which leverages the special hardware to detect the data race, but it's not general to all kinds of data races. Okay, so conclude. In this talk, I introduce a new concept called live program analysis, which is tailored to the subtle and serious problems, in particular the memory vulnerabilities and the concurrency bugs. And it has the advantage of both, in terms of both precision and practicability, since it incurs no false negative or positives, and help prevent the attack and reproduce the bug. Definitely to implement or to realize live analysis is challenging, in particular with respect to aspects, right? One is overhead, another is latency. So we tried some ways by leveraging the hardware tracing module and also the pipelining and the parallel analysis to achieve these goals. In the future, I think the live analysis is feasible, and we can try different ways to implement it. For example, we can try some ways at the level of compiler. From the for the just-in-time compilation, we try to optimize the instrumented subjects. So in this way, we can also may reach the same goal. Yeah. Finally, I have to make acknowledgements to my students, my former students and the current students. I think the idea is discussed by all of us, and the main implementation work are done by them. So thank you. I would like to answer the questions.
Okay, let's thank Professor first. Yeah. Any questions? Well, okay, you go first.
Okay. Thanks for the nice talk. I have one question. Since there is a latency between tracing and reporting, so how would this analysis can detect attack that happens at the gap?
I think, yeah, this is interesting. I think during our submission, we had a lot of similar questions from the reviewers, especially, for some like timely requirement scenario. This is very critical. But we have to see that, yeah, for this particular, question, the current solution, like the hard-tend or hard race, is not really solve this problem. That's why I mentioned another way is try to, whether we can do some attempts from the direction of compiler optimization. In that way, we don't use the decoupled approach. We can, therefore achieve the timely reporting. Yeah, that would be, some opportunities we are trying to looking at.
Okay, thanks.
Okay, I have two quick questions. Can you go back to the evaluation part for the second one? Yeah, this one.
Okay.
So can you detect the data race bug every time? I mean, with your work.
So in this evaluation, we just, frankly, we just use some common way for the effectiveness detection. It covers several kinds of data race related bugs. For example, the double free, corrupted log, assertion crash, etc. So for these bugs, our tool can detect all of them.
Yeah. I mean, when I run a program, maybe the bug is not triggered this time.
Oh, I see. In this particular, experiment, the bug actually is guaranteed to be triggered during one run.
Okay.
This is kind of something done by the designer. Yeah.
Oh, okay. And can you go back to the last? Oh, yeah, this slide.
Mm-hmm.
For the overhead, there's some negative percent.
Because the overhead itself is quite small, is marginal, so it could be influenced by other factors such as the thread interleaving or the different random variables.
Yeah,
that's why
but
it's not stable.
But the 8% is a little bit huge. I mean, for the performance.
Yeah, that's zero. You can check now. Our column is a column by the card, right? It's also like the negative 5%, 4%. Yeah, I remember my student checked this by many times, but it is still not stable. We just directly report this number.
Okay. I mean, maybe there's another opportunity to optimize the performance of multi-thread program.
I think I didn't show the absolute execution time here. For those subjects which has the pretty weird negative numbers, usually the time is pretty short.
Okay.
Yeah.
I see. Okay. Thank you.
Yeah.
Thank you, Professor.